Bohr interpretation of the wave function, which is the probability density. Which is the wave function square. So this is Bohr interpretation. Actually, Bohr interpretation very much conform with what we call the Copenhagen interpretation of quantum mechanics. Later, if you take the master in applied physics, in applied QM, applied quantum mechanics, I will teach you many different interpretations of quantum mechanics. So this interpretation of quantum mechanics is like the Quran, whereby mufassirin, so many mufassirin. Okay, ayat ni sama, tapi tafsirnya berbeza. So quantum mechanics, you describe a same phenomena, the same Schrodinger equation, but interpretation different. So this Bohr interpretation of wave function squares probability density also has a different connotation for different interpretation. Okay, so but it matches very well with Niels Bohr, the originator of this quantum mechanics, the so-called Copenhagen interpretation. You will see later that as quantum mechanics is being applied in different fields, they found that you can have a different interpretation of quantum mechanics, even from the same Schrodinger equation. In fact, for the case of what you call de Broglie-Bohm interpretation, what modern people call Bohmian mechanics, you need another equation to describe the evolution of the wave function, the so-called guidance equation. So satu approach yang berbeza daripada just Schrodinger equation. So so then the meaning of probability also change. Little bit lah, not very much different, but it has a philosophical punya value lah. So this, we know that this is invariant under if the wave function psi become a psi dash equal to E I Q lambda psi. Of course lah, when you square the psi dash, the E to the power of I multiply with its conjugate, which is E minus I Q lambda. So that's finished. And you will see also that I d psi dt, which is the Schrodinger equation, minus 1/2m del square psi, also doesn't change. If you change from psi to psi dash. Okay. Similarly, the what you call the current, which is J, which is psi star del psi minus del psi star psi, this also unchanged by psi becoming psi dash. So that whole thing. This is what you call so this imply what you call global invariance, global gauge invariance. Global gauge invariance. Now, to make it local, we can make this lambda here, which is this Q lambda. Usually, I mean, why there are two variable there in the I to the power of Q lambda? Usually, if you remember, anything that involve e to the power of I something, you remember about Fourier transform and so on, okay? Where you use a lot of this. And usually these are dimensionless. So Q and lambda are conjugate variable. Okay, contohnya energy and time, those are conjugate. Momentum and momentum quantum number and position and so on. So you will see that Q lambda is dimensionless. They are conjugate variable. But what is important to make the invariance local, it's very easy. You choose, say, lambda is equal to some lambda to the as a function of r and t. If it is just without any dependent on space and time, then it is global. But if it depends on space and time, then it is called local. So this dependent make it local invariant, gauge invariant. Now, how about so far? How about making what you call it, Schrodinger equation invariant under this local transformation? I mean, this is kind of a back of envelope calculation. Meaning you already know the answer. You will see that if you make this Schrodinger equation I d psi dt equal to, of course, this doesn't change because this is a free particle, okay? Equation, Schrodinger equation for free particle. But once you involve charge, then you can make also a kind of gauge invariant, but locally. So this, for example, if you write like this, minus I del minus Q A square psi plus Q B psi. What is A? Is the vector potential, and B is the scalar potential, and Q is of course actually the charge. So this one, these are invariant. Under A becoming A plus del lambda. Now instead of using alpha, we use lambda, yeah? And then V becoming V change to V minus d lambda dt. So under this is invariant under this change. And this we can later we will go into the detail of this Schrodinger equation involving charge. And this actually give charge conservation. Later we will go into detail when we deal with EM force, strong force, and so on. from the Feynman diagram. Okay? And then later you will see that the invariance of this equation prove the existence of photon, which is a spin 1 gauge field. And you can see, you can use the same equation but from a specific Lagrangian to derive this Schrödinger equation to derive a spin 1 gluon field for the strong interaction. So kind of a analogy between the EM and the strong force. So anyway, so let's go slightly in more detail about this. I mean the symmetry. Okay. Remember that when we first write or we first introduce the symmetry operator U, I mentioned that U is unitary.